Well, hello everyone. Thanks again for those of you who have decided to join in live on this YouTube stream, and for those of you who are downloading again off one of our accounts, either off iTunes or SoundCloud. Welcome to the next episode of Meet the meQuanics. Today is our 30th episode, which is great. We've managed to do 30 of these things within the year. We started this podcast series a little under a year ago, back in March of 2016. And I'm quite happy with both the reception that we've gotten from this and the level of participation that we've managed to attract from the quantum community worldwide. And that being said, for our 30th episode, I'm pleased to have Professor Jungsang Kim from Duke University in the US, who's agreed to sit down and give me an hour of his time to have a chat about ion trap quantum technology and what's going on with his work. So Jungsang, thanks for joining us.
Glad to be here. Thank you for inviting me to have this opportunity.
So usually the way I get these things started with everyone is to just sort of launch into a bit of a bio of yourself, sort of how you came about working on quantum technology and what kind of stuff you're actually working on.
Sure, absolutely. So I started actually my graduate work in quantum optics. And this was in the early 1990s when I came to Stanford to join Professor Yoshi Yamamoto's group. And I actually started in his group in early 1993. And back then, quantum computing was not quite a strong research field yet, although I think my advisor had interest from the 80s thinking about quantum computing as a computational technology. Mm-hmm. My thesis work was mostly in semiconductor-based quantum optics. We were trying to make small devices, light-emitting devices that can generate non-classical states of light. More specifically, I worked on semiconductor laser squeezing and single photon generations and detections from mesoscopic, very tiny light-emitting diodes. Mm-hmm. But it was a very exciting times. We had some very interesting group of colleagues in my group back then. For example, Ike Chuang was a graduate student with me at the same time, and he was very much interested in quantum optics implementation of quantum logic gates even before the Shor algorithm was discovered. So all of that boom in terms of early discoveries happened right in the middle of my graduate career. But my focus was very much on looking at quantum optics effects in both photonic and electronic systems, and that was my thesis work. I finished my work in late 1990s, and then I actually left the field of physics. I went to Bell Labs. And there I started working on much more practical technologies. More specifically, I worked on optical communications, and we used these micro machines to build large-scale optical switches. That was very hot at the time during the telecom boom in the late 90s and early 2000s. So I worked in optical technology for about 3 years, and then it turned out that the telecom bubble actually popped.
In the early 2000s.
Yeah, in the early 2000s, that was 2002. And then I spent some time looking for a contribution in the wireless cellular phone technology. So because the Bell Labs was working on base stations, I worked on some cellular communication technology. And that's where I actually ended up learning a lot about digital signal processing and nature. But that's when I also started thinking about the possibility of moving back to academia to work on something that is a little bit more longer term rather than working in a mature communications industry. And very fortuitously, there were some of the ion trap groups and researchers at NIST have approached Bell Labs, and Richard Slusher, who was our back then the director of our optical physics research department, and I started looking into the field of ion trap quantum computing. We started just browsing and reading papers, and had a little study group on the side trying to understand what the topic was all about. And that was actually in the early 2004. And that summer in June, I left Bell Labs and joined Duke University. but it was between the January and June, Dick and I read enough, and we had enough ideas to bring along the lines of bringing new technology into this ion trap quantum computing field. Although neither of us had any experience working with atomic physics, I think we decided to make a jump and change our careers. Independently, Dick stayed at Bell Labs and got into this field, and I came to Duke and started thinking about these problems and decided that was going to be my major field of research. And I spent a lot of first maybe 2 or 3 years really learning what this technology and the experiments were all about. I was very fortunate to benefit from the generosity of Dave Weiland and Chris Monroe and all the researchers in this community who are very eager to educate people like a novice like myself about the challenges of the experiment so that we could come up with interesting technologies.
I mean, it's kind of an interesting sort of narrative as to sort of, you came back into quantum computing and, you know, you got to pick. You get to say, well, what technology am I going to be interested in? What technology am I going to work on? And obviously you've fallen into ion traps. What motivated this? Was it just the people that you knew, or was it a particular sort of aspect of ion trap technology that you found attractive? I mean, why didn't you go into superconductors or linear optics or something like that?
Yeah, that's an interesting question. I think part of that is serendipity. Part of that is how things unfolded in terms of me getting exposed to. Us at Bell Labs getting approached by the ion trapping group. But I think more importantly, I think as we looked into how these experiments are done, part of my experience and learning at Bell Labs was really trying to build much more integrated optical systems, right? Mm-hmm. So the electronic systems, of course, we know the integrated circuits is a highly scalable and integrated technology. Whereas, back in those days, the fiber optics and lasers were not like that. Although, the telecommunications industry really were demanding the higher levels of integration for optics and photonic components, they were not being printed just like silicon chips were being printed. We just did not have that level of technology. Mm-hmm. But people did think a lot about, leveraging microfabrication techniques and array technologies. People make big fiber arrays using silicon as a base plate, defining by lithography and etching where the fibers need to be placed. So there were just a lot of, more of a assembly type technologies that were really being developed in that community. And I really think the big optical switch that we built is really a combination of those technologies coming together to build a reliable and complex systems that with robustness of a commercial deployment. So I think when we looked at ion traps, it is true that we actually read some papers, but we did not actually decide to read all the papers, survey all the technologies, and pick one. We certainly did not have the luxury of doing that. But I think when ion trap came in and we were approached with the ion trap community and we started reading and thinking about this, the more and more we were convinced that there was a lot of technologies that were being developed in the telecom industry that could come in and really make a difference. Right. And that prospect itself was exciting enough, so we got fixated on that.
So, I mean, where do you see the technology now? I mean, we've had an ion trapper on the podcast before, Mike Beerchick from Sydney, who sort of give us a bit of a background on the technology that he's building. We've had all kinds of different guys come on and talk about stuff in superconductors and linear optics and silicon. Ion traps, I think, is fairly safe to argue is one of the big two technologies that seem to be working at this point, along with superconductors.
Yeah.
Where do you see, I mean, the work that you do sort of in place when it comes to big corporate efforts such as Google and IBM, who have seemed to push along the superconducting route rather than the ion trap route?
Yeah, so I think my contribution for the past 12 or so years was mainly two aspects. One is bringing new enabling technologies that can improve either the performance by orders of magnitude or improve the stability of the systems. But the other was much more of a looking at the whole experiment that's what it was 10 years ago, and thinking about turning that into a viable system. Right, so when you turn an experiment, I mean, typical ion trapping experiment, if you have been into one of these atomic physics labs, they typically have a huge optical table in the middle, right, with lots and lots of hundreds and hundreds of optical components on the table, and instrument racks, overhead racks full of equipment that's driving the thing. And these are all very carefully tuned. That requires day-to-day maintenance from graduate students and postdocs to run the system. And that's arguably that's the way things are done for decades in atomic physics. But then you look at these transmission systems, WDM, long distance transmission systems, where you have hundreds of lasers all in an instrument rack. Right, all frequency stabilized and modulated, and you have fibers coming out, and they look really more like a rack full of instruments that are much more contained in a system, right? And so just looking at the picturing between these two, you can take the complex ion trap experiment and then identify what the key components are needed to run that thing. And then each of those key components can be defined as a subsystem that somebody can assemble in a much more compact form. So you can actually now take that complex experiment and start to define them into subsystems that you can assemble into a more complex operational system. So that systems design approach is really what I was interested in thinking about, right? So I think that those two are the focus of the effort that I've had, and in my mind, the superconducting quantum computer would not have passed the test of quote unquote product ready system if the closed cycle dilution refrigerator were not invented, right? If you had to transfer helium every day into your quantum computer, I don't think anybody in the industry would have thought that would be a viable system. But there are some very seemingly mundane progress that converts a scientific experiment and make people believe that it could be a commercial product, right? So I think in ion trapping there are many elements like that that we've really enabled over the last 10 years. In a very carefully decided way. I mean, there were things that we thought we had to fix to break that perception that this will never be a product. It's always going to be a scientific experiment. Two, yes, this could actually be turned into something reliable and mature. I think one of that is these microfabricated silicon traps. That is, over the last 10 years, it has matured so much that I think that is the best platform to do most quantum gate operations. Although there is a little bit of remaining issues in heating rates and things like that people have to iron out. But I think everything we learned today, everything we have learned to date, really gives us all the confidence in the world that they are the perfectly manufacturable platform for building traps. And then, the stable laser systems, how do we actually implement all these gates? How do you control all the pulses in a fairly programmable way? There's a lot of digital control electronics that were developed and matured over time. So as these components do come together, I think today we are absolutely convinced that we can break down our ion trap system into a series of subsystems that somebody can put together and test and verify independently, and then we can just assemble them and turn them into a much more robust quantum computer type system. So
sorry. So I just wanted to just clarify, because you do a lot of work with Chris Monroe's group at the University of Maryland.
Sure.
So correct me if I'm wrong, but his group's sort of more responsible for the direct fabrication of the ion trap qubits themselves, and you're sort of more in the area of all of this control infrastructure that sort of has to sit around the computer. We've got to miniaturize it, package it, automate it, et cetera, and you're more responsible on that side.
Well, it's really not that simple. I think our operation over time have really permeated into each other. So there isn't a very clear boundary like that. I think both what he's doing and what I'm doing, we always have to think about systems. Whether the system happens to be assembled in a way that a typical graduate student would do on an optical table versus more professionally assembled, I think those are really small changes. I think if you want to really think about the division, quote unquote, division of labor between Chris's team and my team, I think Chris really has been focused on demonstrating the quantum control protocols, right? If you gate protocol, or if you want to think about how to run a 5-qubit system, he's really been pioneering the implementation of those protocols and gates and algorithms on the forefront of that research area. I'm more thinking, instead, following a step behind and say, okay, if he's doing this state detection, for example, how do I do it much better and faster, so the performance gets better? If we're talking about logic gates, how do I add another 9 or 2 in the fidelity to make sure that we have much higher performance? And usually those higher performance comes with a better and more stable system design.
Yeah.
Right? They're not necessarily inherent to the qubits. I think most of our infidelities and limitations really come from the control fields that we use. Right? We're not limited necessarily by the qubits themselves, the ion qubits themselves. All of our performance seems to be limited by the stability of the lasers and the level of control we can have to make sure that each control pulse is perfect. And those are, in some sense, you have to diagnose your system and if there is a if there is a significant flaw in your system that makes certain parameters unstable, you have to start from scratch and think about how to engineer the system so that they're much more stable. And then, so I think I've really been adding 9s to our fidelities, cutting down orders of magnitude in speeds at which we can do things, or cutting down orders of magnitude, meaning cutting down the time it takes to do certain operations, whether it's state detection or photon-based entanglement generation. So we've really, if it's a factor of 2, I don't think we're picking the right approach. We're really talking about how to improve it by 2 orders of magnitude, right? Because I think those are the engineering progress that we need when applied to the protocols that Chris is developing and demonstrating, will lead to processors that can do much deeper gates over a much larger number of qubits. So at the end, when it comes to the algorithm execution capability on a bigger system, I think these numbers of 9s that we add really make a difference. Right?
So it sounds as though your focus really is on the computational side. You're really interested in building a quantum computer out of this system.
Absolutely.
But in terms of sort of shorter term goals, I mean, do you sort of go down any other tangents in terms of viable quantum technology that could be done on the 10 to 100 qubit level?
Yes. So I think if we look at the research that I do, and again, I think what Chris does also highly parallels, because we have a lot of collaboration that overlaps. I think the first and foremost focus that we have is how do we design a programmable quantum computer that has a much larger number of qubits. So in Chris's lab today, we have a 5-qubit system. He has a 5-qubit system operational. The fidelities are pretty decent, but they're nowhere close to the state of the art in the ion trap community. But the level of complexity that he can handle is really state of the art compared to any other ion trap groups that we can think of. I think we actually are putting together our next generation system. I think we are planning on getting to about maybe 10 to 15 qubits sometime this year. And then, as part of our most recent collaboration, we've actually taken all the knowledge that we think we know to take our control systems and make them more stable. And these are mostly stabilizing the laser beams that actually hit the ions. I mean, putting all of that knowledge together, Chris and my team have really designed the next generation system that will scale up what Chris's current system is to something on the order of maybe up to 25 to 30 qubits. Right? And that system has been fully designed. Again, in this case, we have done the designs with our subsystem vendors. We've actually found some strategic partners who can actually construct these subsystems in a much more robust way for us, right? So when we say laser systems, rather than our students going into the lab and building laser systems, we're going to have some professional engineers package all the laser systems to spec and send it to us, right? So we actually have done these kinds of arrangements and collaborations with some of our partners that are suppliers to our subsystems, and that system is actually coming together in Chris's lab today, and we're hoping that will be up and operational again sometime this year. So
and this is surface traps and shuttling, or is it still?
Well, for now, these will. I think our goal is to make sure that we use microfabricated traps.
Mm-hmm.
I think very first version of the system, we probably will not be doing a whole lot of shuttling. Although in this recent IARPA program that Chris and I are working on, we're supposed to our goal is to demonstrate quantum error correction.
Mm-hmm.
And for quantum error correction, you actually have to read out some of the ancilla qubits while keeping the data stable. And for that, in the ion case, if you're making measurements on some ions, we have to bring in resonant photons to actually destructively collapse the quantum states, right? It's not destructive, it's non-destructive, but we have to have a dissipated process of measurement. And those resonant beams can actually hurt the data qubits.
Mm-hmm.
So we are actually working on the traps that we are using today. Will have the ability to pull those ions and shuttle them away, so that you can actually make the measurements without necessarily killing the data qubits. So from that perspective, when we're doing a measurement in conjunction with retaining data, I think we're going to be introducing some shuttling capabilities, and those capabilities have been fully verified, at least in my group, and also quite operational in Chris's team.
So this would be a 25-ish qubit experiment in the next year or so.
Well, I think to get up to 25, I think our system will absolutely be capable of trapping 25 ions.
Mm-hmm.
Whether we can do a full controllable quantum operation on 25 qubits, I think that will probably end up taking a little bit more time. I think we're going to take small steps at a time. So we'll probably get to 10 or 15 this year. But absolutely, the hardware that we build is going to be capable of expanding all the way up to about 30 or 32 qubits.
Okay, well, that should be pretty cool. I mean, if you can get even 10 to 15 during the next 12, 18 months, that would be quite an effort,
yes.
Especially if you can do it in this sort of fully programmable way like the 5-qubit device already does.
That's right.
So,
yeah,
I mean, this sort of... I'm sorry. No.
And excited.
So this sort of jumps into the next thing I wanted to ask you about, because you and Chris have also founded a recent startup, ionQ, is that correct?
Yes, that's true.
Now, we've seen a few of these pop up recently. I mean, Rob Shokoff's group's got one in superconductors. Obviously, there's Rigetti Computing with Chad Rigetti, who came out of that group and decided to go it alone. I'm interested into sort of what the mandate is for ionQ, because I know, say, for example, Rob Shokoff's little startup, it's quantum computing and quantum technology focused, but at the moment it looks as though it's largely based around sort of fabricating and selling pre-packaged elements for doing superconducting quantum computing. In contrast, say, to say Rigetti Computing, which seems to be wholly and solely focused on pushing forward and building a quantum computer. How have you structured ionQ, and what's ionQ going to be doing for the next couple of years?
Yeah, so I think it is my belief and Chris's belief as well, and that it is time, actually. We are actually ready to try to construct a full-blown quantum computer based on trapped ions. As part of this IARPA logic program that we started back in late March, early April last year, we went through the process of designing a system that we think is well defined as in terms of key subsystems and the critical quantum features that's needed to do high performance gate operations on them. So we went through this system design. Again, as I said, that first system is currently being put together with a goal of probably being operational by either late spring or early summer. And designing and constructing that system gave us a lot of confidence that that such a full-blown quantum computer with ion traps can actually be constructed. We are quite confident that this could be done. Now, how well it works and how easy it will be for our customers or users to interact with it. I mean, those are some of the new developments that have to be done. But in terms of the hardware itself, getting up to, as I said, up to 32 qubits, I think we have a very solid blueprint to build that. So I think developing that into a more commercially viable and reliable system is basically what ionQ's effort will be in the next couple of years.
So it's fair to say that ionQ really is in this for the quantum computing game.
Yes.
And you are, as far as I know, you are the only ion trap startup that I'm aware of. Is that correct?
As far as I know.
Yeah, I think you're the first one that I know of with ion traps.
Yeah.
So, I mean, when you were putting this together, and obviously you have to raise money and you have to do all this stuff, how is the sort of investment sector looking at quantum computing now? You must have had lots of conversations with these people. Are they excited? Are they knowledgeable in where we are? Or is it sort of, they still have to look at what's going on through the newspapers rather than through the lab?
Well, so, I mean, I've actually never seriously interacted with the investment community until just about a couple months ago. But I think what I have learned is, they are some of them are very excited, not all of them, right? There is, just like we have all kinds of researchers with different kind of long-term and short-term goals. I think investment community is very much like that too.
Yeah.
There are certain investment firms who really like to take long-term bets.
Yeah.
Right. So this is where, yes, the business risk is there. Yes, the technical risk is there. But if somebody is able to do it, then potentially the value that you can create is very large, right? So there are firms who are interested in that kind of a long-term bets. I would say not all firms are like that, but I think many firms with a long history of success actually have that view. So among those firms, I think we've learned that there is a very significant interest in finding the right technology and the right people that they want to invest in. I think the technology risk, if the technology risk is too big, I think the community will say, okay, we'll let the research community work on this a little bit more until a more concrete picture can be found. But I think the progress that was made over the last 5 or 6 years through the IARPA MQCO program and so on, I think a lot of that technical risk has been addressed, and people, a lot of us, the researchers, are starting to be convinced that we're ready to build this thing, right? And once they see that confidence from the technical side, then the next question is, what is the business risk? And business risk is something that the investment community understands very well. Right? They may not understand quantum mechanics, but if there is a good group of technology people who says, look, I think the technical risk is manageable, and then they can really think about how to build a business, and that is an area they're quite comfortable with. So I think it's come to a point where some of those investment firms that are willing to take a long-term bet, if they meet with a group of technical technologists who feels that this is something they could do, then I think the opportunity is there. Now, obviously, they do a lot of due diligence, right, to make sure that the people have the credibility and the track record, and also that the technical approach is sound and feasible, and all of that. And it's, again, they're not investing so you can write papers. They're investing so that you can create some value, commercial value, right? But I think people have and I also noticed that they all talk to each other too.
Yeah, that's been my experience too. They're more of a gossip farm than the physicists.
That's right. So I think the fact that there are some startups that are getting a lot of traction, I think indicates that the confidence is growing in that community as well.
I mean, it's interesting. This is somewhat of a redundant question because you've started a company, but I often ask people as to are they seeing this this kind of quantum technology, this stuff moving out from the academic sector and into the private sector. So I won't bore you with that question. You've already answered it. But what I'm interested in, certainly because you've taken the risk and you've decided to at least, wade maybe ankle or knee deep in the private sector at this point, is what was the tipping point for you when it came to the technology? At what point did you realize and sit down and say, okay, now it's time?
Mm-hmm. Yeah, so as I said, before getting into this field, I was very much in that sector, right? I was very much into taking technology and turning into products. Mm-hmm. I've actually developed technologies that turn into two different technologies that turn into products in my very short 5-year stint at Bell Labs. I think when I came into academia, it's not because I was fed up with that. I wanted to do similar things, but in a technology area that was a lot more disruptive rather than very mature market. And quantum computing, I felt, was one of those, right? 10 years ago, it was not at all clear whether there would be a commercial path. But my interest has always been, what would it take to take this technology and turn it into something that has a commercial traction, right? I think for the last 12 years, I've always had that as a goal in the back of my mind.
Yeah.
So that naturally steers a lot of the research activities that we have, research programs that we put together, proposals that we write to governments about, some of the system scale things that we can do. And over time, I think our effort has really pushed along those directions. Now, when you say, when did you think that we felt this was the right thing to do? I think when Chris and I actually started our company almost a year and a half ago. Mm-hmm. And back then, of course, we had some vision of how we thought the ion trap quantum computing, especially the modular version of it that we explored in the IARPA MQCO program, was a really viable architecture, right? Yet, yes, there are some performance issues, and we had to improve the technology by quite a bit. But we didn't see any fundamental limitations of why we can't scale the technology, right? Until we actually built a big enough quantum system. But nobody has control over a big enough quantum system to see if quantum mechanics will behave, in a scalable way or not, right? Mm-hmm. All indication is that quantum mechanics will scale, and as long as that quantum mechanics scales, and what we can predict is, can our technology scale? So we were quite convinced in about a year and a half ago that the modular quantum computer architecture we had with ion traps were actually quite scalable. And this scalable, not just in the sense of we can put lots of qubits together, we have each and every technical element that's needed to control this to a scalable level, right?
Yeah.
So that's when we founded the company. We thought it would take us many years until we can put a convincing prototype together. And we were thinking that this IARPA logical qubits program would be a really good opportunity to really push the technology along those directions. But I think the first few months of our design activity, putting together a blueprint for the system that we'll put together for this logical qubits program, when that went really well, and we were very fortunate to find the right kind of partners to work with. These technology developers, right, mm-hmm. that can build technologies that it's really hard to do at a university. Then I think we got enough confidence that this was really time. We can actually do this sooner rather than later. So we ended up, launching the actual operation and quote unquote product development or prototype development within the company, mm-hmm. Several years earlier than we had originally anticipated.
I was at the moment, so it's sort of a bit still sort of half university, half private, or I mean, do you delineate the two, that you hire basically for ionQ and then sort of your operations at the university go on sort of roughly independently? I mean, how's it structured at this point?
Well, yeah. So I think the company operation will be very independent, right? But I think there will be some technological overlap, right? Obviously, the confidence of the system design really came from our university effort, right? But I think all of our university-funded programs have project goals that we have discussed and agreed with our sponsors.
Because I mean, the major reason that I'm asking is because I talk to a lot of students and a lot of younger postdocs about academic careers versus private careers, and now that the quantum technology is slowly moving into the private sector, this now becomes a viable career pathway for a lot of people that we know who are coming up through graduate school and early postdocs at this point.
Absolutely.
So.
Yeah.
I mean, this obviously would be a goal for you, is to sort of extract from this this group of training that occurs worldwide when it comes to education and developing skills in both theoretical and experimental quantum computing.
Absolutely. So I think the reason that Chris and I couldn't start a company maybe 5 years ago was there weren't enough trained staff members that we could hire to actually do this task. Right. I mean, there were some, but there weren't enough, and people with the right kind of mindset who are really, a lot of the PhDs that was trained in this field, many of them think about academic careers. If not, they go out, and because there was no such industry, they would go out and do other things. They move on to other things.
Yeah.
But I think this just within the last few years, we felt like there were really a good group of really well-trained scientists who had, in my mind, who had the engineers in them.
Yeah.
that really wanted to do this rather than look for an academic careers. And we've actually, Chris and I have been looking out for these kinds of people for many years. And over time, we've actually really recruited them into our university programs. And I think they will eventually, as the university programs, progress. They're not there forever. So I think many of these staff members that we have recruited will eventually transition into the company.
I mean, do the groups that you guys run at Maryland and Duke, do you try to restructure them? The British are doing this quite well at the moment when it comes to their doctoral training programs. That it really is about training for a new technology sector. Is that happening? In your neck of the woods?
Well, I think if you think about PhDs in physics, right? Their primary path is to go get onto the academic career paths. I would say, whereas if you look at the PhDs that we trained in electrical engineering over the last 50 years, right? I mean, these are the people who went and made Moore's law happen. Right? The majority of PhDs out of our leading engineering schools, I mean, of course, many of them do become academic professors, but a vast majority of them move into industry. You think about how many PhDs there are in Intel and Microsoft and all these industries. And I think I set up my group in an engineering department. And I don't necessarily think of myself as an ion trapper. I think of myself as a system developer, and I train my students and postdocs so that they can build systems. I've trained them to build gigapixel scale cameras, which is not quantum at all.
Right.
And I think that I'm training these students so that when they were asked to build a quantum computer, right? They would know the engineering design rules and principles so that they can go build a complex system like this. So I've always viewed my group as a systems group. We just happen to be most interested in quantum computer as a system that we want to build. So from that perspective, I've always trained students so that they could move into, and many of my students actually have transitions into industry, because once this skill set is gained, whether you worked on quantum computers or gigapixel cameras, right? The skill set to really dissect the system and come up with a design that's robust and putting it together and testing it and debugging it and improving the designs. There is a very systematic way of building systems, right?
Yeah.
So in a sense, I've always been training people to do that. Many of some of my postdocs and students I've worked together are actually exactly tasked to build that, either for the university systems that we're building in the context of the logical qubits program, or some of them have already moved on to the company and they are going to be building a similar system for the company. But the system that we build at the company will actually have its commercial mission as the goal, whereas the systems that we build in universities will be really used to meet the goals of the sponsors programs.
So I mean, the major point being is that a lot of students ask, and we talk about academic pathways, and these days I think more than ever becoming a professor is getting harder and harder and harder. But this shouldn't dissuade students from getting into quantum technologies at the grad level, because there is a very significant industry that's starting to arise.
Absolutely, that's absolutely true. And I think professorships getting harder should never be. I don't know. My personal opinion is that should never be the goal of why you pursue a PhD, right? Although I end up becoming a professor, right? I mean, when I left academia, I went to Bell Labs. I went there as a postdoc, but within a year, I was convinced that I didn't want to become a professor.
Yeah.
Right. So the product development and the industry was going so exciting that I was determined I was going to stay in the industry. Now, of course, that view changed after a few years. But I think I would always like to argue that the professional career path at industry is actually extremely exciting, right?
But I mean, the point is now that they can take that pathway and still be embedded within quantum information and quantum computing.
Absolutely.
Might be the original passion that got them into it.
Yeah, I think it's only going to grow. And I think if the trend continues, I think there will be a demand for universities to actually train people for the industry rather than for the academic world.
Well, that seems, especially in the UK, that seems to already be a thing.
Yeah, and I'm not surprised, and I think that trend hopefully will continue to grow. I point to the role of say Stanford's engineering school in the 70s, 60s, 70s, and 80s in building Silicon Valley, right? I think and that's how the talented people that were trained through that type of programs is really what made Moore's Law in Silicon Valley happen. Of course, there's a lot of uncertainty whether quantum will end up becoming that kind of an industry or not is yet to be determined. But I think we can still put a lot of talented people out there, and whether this mission of building a quantum computer succeeds or not, they will learn a lot in that process and become a very valuable engineers with commercial focus.
Yeah, no, I completely agree. And, in that way, I've always tried to be fairly optimistic when it came to students, is to say, no, the future's not as dim as you think if you pursue this kind of education. Don't let the pessimism of certain other people stop you from doing it.
Yeah, no, I think it's always exciting, right? And the students should not necessarily, students should not necessarily worry about exactly what they're going to do after they finish their PhD.
Yeah,
I think those are. I've never actually predicted where I'll be, more than 6 months ahead of time.
Well,
I always ended up in jobs that I never imagined.
Yeah, well, I've been stuck in Japan for 10 years and I never saw that one coming.
Yeah, so
you never know. So, I mean, we're getting up to 45 minutes now, so we'll sort of start to round this up. But as usual, when I get people onto the podcast to have a bit of discussion, I like to hold their feet to the fire a little bit and sort of press them for a prediction in the next 5 or so years, either in general with the entire field itself, or more specifically with your efforts and what you hope to get done with ionQ and ion trap technology within, say, the next 5 years to a decade.
Yeah, sure. Actually, let me start by backtracking a little bit. I think when I got into this field, in 2004, The consensus in the community was, practical quantum computer, that's decades away, right?
Mm-hmm.
So 50 years away, 30 years away. I actually never felt it was that far away. If I had felt that it was 50 years away, I don't think I would have started working in this field.
Well, you were a minority.
Yeah, I was an absolute minority, probably one of the most optimistic persons. But being an engineer, as I said, I think I'm a system construction is my passion. Being an engineer, if I wasn't convinced that we could do this in the next 15 to 20 years, right? I am not sure if I've taken this path.
Mm-hmm.
So I've always been very optimistic, and I continue to be the case. I really think that a programmable quantum computer, we already have one. IBM has a publicly available quantum computer, a programmable one at
Mm-hmm.
5 qubit levels. I think within the next 2 years we'll have quantum computers in the 30 to 50 qubit scale that are programmable. I think that will become available in the next 2 to 3 years. Mm-hmm. I think within the next 5 years, again, unless quantum mechanics tells us that handling these large qubits has more complexity than we recognize today, right? Unless there's something about quantum mechanics we don't know about today.
Yeah, something kicks in when we get to 50 qubits that we had no idea existed.
That's right. So my prediction is we will get to complexity levels where the quantum systems that we can control will be way beyond what classical simulators, computers can simulate or calculate. Mm-hmm. I think we'll get to that point absolutely in the next 5 years, or we'll discover that quantum mechanics does not allow us to do it. And my joke is the consolation prize for that will be a Nobel Prize, right? It will be a new type of science we discover.
Yeah, that's true. That's true.
but as long as quantum mechanics is true, and we can continue to push the technology development, I think what people refer to today as quantum supremacy, or building quantum systems that cannot be simulated by classical computers. Mm-hmm. I think that will happen in the next, very optimistically in the next 2 years. Mm-hmm. Even the most pessimistically, I think in the next 5 years, unless the bottom fall out of our industry, right?
Yeah, no, I think we're past that point now. Yeah. When I finished my PhD, I thought maybe the bottom would fall out of this, but so far it hasn't, and I think it's gone the opposite direction.
Yeah,
which is good for all of us.
Yeah, so I think whether it happens at ionQ or any other, I think it could happen at the university, but I think once the industry, whether it's big companies like Google and IBM or small companies like us, mm-hmm. Once there is a highly focused engineering and technology effort, things will move at a pace that we're not used to. And that's been the case whenever a scientific project or concept from academia transitions to industry.
Yeah.
Things will move at a very different pace, and we'll be surprised what we face with this. But I think one of these companies will get to that point.
Yeah, I mean, dumping 200 or 300 engineers on a project is a hell of a lot different scale than even a large research group, which might only be 20 or 30 people.
Absolutely.
So finally, before we wrap it up here today, is there anything you want to plug, anything you want to advertise, anything interesting going on at Duke or anywhere in your region anytime soon?
Well, sure. I think, well, if I am to make a statement, I think ion trap is a real technology. I mean, I think people can readily see that, semiconductors or superconductors, because we have seen them made at scale for classical processor purposes. But I think the key, what I'd like to emphasize in the ion trapping field is it is true that our qubits are extremely robust. We have very good qubits. Mm-hmm. And it is also true that the scalable assembly of this kind of a thing has not been very efficient to date. Mm-hmm. But I think I am convinced that we are actually well on our way to inventing the right kind of technologies that will eventually make this scale. Right, so I think the focus of our effort is inventing the technology to make it scale, rather than trying to improve our qubits, because our qubits are really good.
Right.
And I think that technology development is a much more manageable problem And as we make progress on that, I think we're going to be able to compete very well with some of the solid state technologies.
Oh, look,
we'll see.
As far as I'm concerned, look, you guys are all doing a great job, and I just want to see this system get built. So whoever gets there first, whoever gets there the best, doesn't really matter to me. I just want to see it on a computer.
Yeah, and I think this is actually, in a sense, a very healthy competition.
Yeah.
Right. And I think it's not like we do talk to the superconducting community a lot. I mean, a lot. And I think there are eventually some real synergies we can use, especially when it comes to maybe user interfaces, how people program these things. Just like you can use the same program on a Mac or a PC, right? It could actually have a very different hardware platform, but if the users can actually relatively transparently use both systems, I think that's going to really help stimulate new innovation in the space. So I think this really is a very healthy interaction and competition, and this is a really exciting time to be in this field.
No, I agree completely. Just knowing what these systems require and the hardware that's necessary to build them, most people are going to interface with a quantum computer just like the IBM machine. It's going to be over the cloud, it's going to be over the internet, and they're not really going to care what the qubits are that are sitting in a lab somewhere on the other end of that internet connection.
That's right.
So once again, I think, well, we're heading on to 50 minutes now, so I think that should be it for today's podcast. So once again, Jungsang, thank you very much for giving me an hour of your time. It's getting late in North Carolina, so I really appreciate it.
All right, thank you. It was a great pleasure talking to you.
Yes, you too. So thanks again, everyone. Again, as I always say, please tell everyone you can about the podcast and subscribe to us on iTunes and SoundCloud. Our next guests are being confirmed right now. As soon as we have dates and times available, we'll obviously put them up on YouTube and our other social media feed. But once again, just keep following us on Twitter and YouTube for any updates. So thanks again. Cheers.